back the test 1 today. And basically, I just want to go through this grading scheme with you briefly, because I don't want you to get too elated when you see your grade, and I don't want you to get too dejected if you see a grade, because right now, if you are choosing test light, this one exam is counting for 40% of your grade. So that's either great news or not so great news. And if you're test heavy, it's 50% of your grade. Whereas by the end of the semester, each of these percentages will be divided by 3 because we're having 3 tests. So I want you to just kind of put that in perspective today. Again, we have 1 quiz so far, so that 1 quiz is either counting 15% or 25% of your total grade. Okay, whereas by the end of the semester, we'll have had 4 quizzes. And your projects are the same, and we've had 1 project. So if you didn't do your first project, then that's a 0 in that 10%. So just remember that each of these have a single average assessment in them right now, counting for 85% of your total grade. Okay, the only percentage not in there is your final exam. So when you see your course grade to this point, when you turn your first page over and you see each of these averages, note that that's because all of what you've done so far is counting very heavily. And like I said, that's either going to elate you or maybe deject you a little bit, depending on, where you are. So the other thing I want to point out is I am obligated, if you've been at GCC before, you know that we have to do what they call midterm early progress reports, and you can do those at any point. So if you have like a C- or below that, then I will be sending out this little report encouraging you to do things like use the math studio before class instead of, sleeping late or hanging out in the cafeteria. Come see me, go maybe set up a peer tutoring. I'll put my recommendations on those. You get a copy and your advisor gets a copy. Okay, so that's called the early progress report. So I'll hand those back at the end of the hour. And I've encouraged some of you to come and see me, like to set up an appointment and come and see me. Some of you, I wouldn't mind seeing you once a week if we could see each other for a half an hour and just kind of go over things and any questions that you have. Colton? 5 homeworks, yeah. 5 homeworks get dropped for your last grade, right? Right now, everything's counting in there. Okay, so today we're going to start the idea of functions, and we're going to be working with functions so the rest of the semester, and this is really one of the key objectives of this course. So you want to start us off, Paul? We're going to talk about relations first. Okay, so we're familiar with how to represent data. If it comes in with 2 variables, we use this thing called an ordered pair. We can graph it, we can represent it in a table, and we can represent it with a model or an equation. Okay, to continue with us here, Tony?
For example, suppose we selected Jeff Green, Avery Bradley, Keith Bogans, and Gerald Wallace from 2015. Boston Celtics prospects. 6'9", 6'2", 6'5", 6'9". You can write this correspondence with names, heights, and the set of.
Yep. So notice this correspondence between these 2 things is a set. Notice we use the braces here. And inside those braces is an ordered pair. You're used to seeing numbers. In this case, we have the person's, the Boston Celtics name, and listed beside it is the height of that person. Want to finish off here, Tony?
The set of word pairs above is called a relation. Relation, any set of word pairs.
Okay. All you need to know about a relation, any set of ordered pairs, any relationship, notice relation, relationship between 2 variables. Nothing special about it, okay? Okay, want to continue, Bob? Okay, so this idea, domain and range, we'll be working with over and over and over again. So whatever you're used to seeing in that first little spot in the ordered pair, what you usually call the X value, is called input now. And that's all the inputs. Notice the set, braces again, the set of all the inputs is called the domain of, in this case, the domain of the relation. Okay, next paragraph. Sandra? Okay, so this was sort of like our reunion idea way back with class 1. So we have 4 people, 2 of them have the same height, 6'9", I believe it was, so we only list that once. These are the elements. Every individual part of a set is called an element. These are the elements of the range of your relation. Okay, so now let's take a look at a visual. So here's a visual. Notice the blue oval represents the domain. It's the set of all the inputs. So here I've put each of the Boston Celtics name. And on the right side, I have another oval that represents the set of all their heights. And what I've done is I've drawn a line, an arrow from the person's name to their respective height. Avery Bradley, 6'2", Jeff Green, 6'9", Keith, and Gerald, okay? So notice you have the 2 people, Jeff and Gerald, are both 6'9", no problem. We're just looking at a corresponding relationship between the domain and the range. All right. So, want to continue on, Caitlin? Oops, did I forget something? I don't know. Here in the ordered pairs? Okay. Okay. Yep. Okay. So now let's fill in the domain and range. So now in the first slot, the first component, our inputs are the heights instead of the names. So tell me what I put into this blue oval. It's going to go into the blue oval. 6 feet 9 inches. Yep, I'll put that in one little box. That's one element. What else? 6 feet 5 inches. And one more. 6 feet 2 inches. Okay. Now we're going to list the range. Okay, so who's in the range? We'll use initials. JG, yep. Second table. Table 2. AB. Table 4 right here. KB. And I'll do the last one, GW. Okay. All right, so there's your domain, there's your range. They're a set of your inputs and a set of your outputs. Okay. So now suppose, well, this is really a fantasy, but suppose that the most valuable player award goes to the player that's listed as 6'9". So you're walking into the locker room and you're looking for the player that's listed as 6'9". Well, first of all, let's do the correspondence. That might help us. Who was 6'9"? Well, who was 6'5"? Which one was 6'5"? KB. Okay, so, and 6'2" was Avery. And 6'9", 6'9" was Jeff Green and Gerald Wallace. So we got a problem, right? If I'm walking in with this heavy MVP award and I want to hand it to the person that's 6'9", I have no way of knowing, okay, who to give it to. Do I give it to Jeff Green or Gerald Wallace? I don't know, okay? So this is an example of a relation that's not well defined. If it were well defined, then I know who to give my MVP to, my MPV award. So let's take a look at a relation that's well defined. Okay, Ethan, want to read this for us? Okay. So a function is a relation. Notice the umbrella would be called relation because it's any ordered pair. A special part of that relation, a special subset of that relation, if you so to want to think of it as sets and subsets, everything is a relation. Okay, every single ordered pair is a relation. A special subset of that relation is called functions. And when we have a function, every input has exactly one and only one output. For each thing you put into the domain, each element of the domain, there's one and only one element in the range. Okay, so let's take a look at our Celtics players again. So let's take a look at the first example where we listed each player's name first and then their height. And the second set, H, we're defining as the height first and then the player's name second. So at your tables, I want you to identify which of these sets of ordered pairs represents a function, and you can answer that with P or H or both, and identify which ordered pairs represents a relation, again, P, H, or both. So talk about that at your seats, and we'll take a look at it in a minute. Table 5, since you were the first to put your flag up, can you identify which set of ordered pairs represents a function? P. And can you tell me why P is the correct answer? Can you tell me why P is a function? Right. Okay, well, let's not do H yet. I just asked about P. Thank you. And let's go back here to our original picture. These pictures often will help you. For each name, notice there's only one arrow going to, the arrows only go into one height for each name. All right, and it's okay that Gerald's going to 6'9", because Gerald, if I put Gerald into my little machine, out pops his height, 6'9". Just like if I put each of your names into the first slot, what will be unique about what comes out in the second slot? For example, your social security number. No other person has that social security number, at least we hope not. Okay, so that's a unique, well-defined function. It's a relationship between two things. Do you have your lecture notes with you, Mason? No? Okay. So P is the answer there. Which set of ordered pairs represents a relation? It's a little harder, this one. Who wants to take this on? Yeah, Cole, Eddie? Excuse me? H. Does everybody agree with that? So H is a relation because why isn't it a function? Why isn't H a function? Why is H not a function? Mason?
Because if you're 6'9",
Perfect, right. 6'9" doesn't have a unique output. 6'9" was the problem we ran into with the MVP award earlier. Is that all you have is H? Who said no? Okay, Alyssa? You could have P also. Perfect, that's right. Both P and H are relations. P is a special relation, a well-defined relation called a function. So the answer here is both sets fulfill the requirements of being a relation, but only set P satisfies the requirement or criteria for being a function. Any question on this before we move on? Are you all set with that, Caitlin? Okay, Mason?
it's not the tab on top of it. When did we get our tab?
At the end of the hour. Okay, so determine whether each of the following relations is a function and then find the domain and range. So I'll do the first one for you. So in the first set of inputs, right here, Phoebe, Amy, and Katie, that's our domain. So you use the braces and you write each element of the domain, which in this case represents 3 names. Okay, that's the domain. And then the range would be the outputs. There's only 2 outputs here, 5 feet, 5 inches, and 3 feet, 1 inch. Let's hope that Katie is child. Okay. Now, does this represent a function? So to answer that, you say, does each one of those inputs have one and only one output? Does each input have one and only one height? That's the answer, if you're brave enough to try it. I see this. Phoebe's height, 5 feet, 5 inches. Amy's height happens to be the same, but no problem, 5 feet, 5 inches. Katie's 3 feet, 1 inch, okay? So is this a function? Yeah, absolutely. Okay, so you continue on with these next 3. Work at your seats. Answer if it's a function, and then define the domain and range of either the function or the relation. Table number 1, would you tell us what you put for each of these 3 components? Your table 1, yeah. Okay, so you use your braces, 0, 3, -2, and 6. Those are the elements of the domain. And the range? 7. And is this a function? Yes, it is. Any questions on that? All right. How about the next set of ordered pairs? Table 2, is this a function? Yes, you're right, Samantha. And what's the domain here? Thank you. And the range, Alyssa? 2, 3, and 5. Right. Okay. And the last set of ordered pairs, Mason? It is not a function. And why is it not a function? Right. 3 goes to 7, and 3 corresponds to -4, which is fine if you're a relation. So this is a relation. It's not a function, because 3 can't go to 2 different outputs. So the domain here is the set of numbers -4, -3, 1, and 3. And the range, if we list them in order like my math lab's going to ask us to, would be what? Nope, not the way my math. Yeah. Yeah. 2, 3, 4. Okay, I couldn't hear you. Go ahead. -4. Oh. 7. Okay. All right. So when we have our next quiz, you think you're going to be able to do the domain and range if I give you a picture like this or a set of ordered pairs? Okay, good. So there you go. 10 points. All right, so we have different ways to represent functions, and we're going to work on all different ways. We can represent functions by a set of ordered pairs. We can represent functions by a numerical table. We can represent functions by an equation or a formula, and we can represent functions, yoo-hoo, by a picture called a graph. So here's a graph. How many elements are in, how many sets of ordered pairs are in this particular function? How many sets? 1, 2, 3, 4, 5. Okay, so, well, first of all, we have to determine whether this is a function or not. It has 5 ordered pairs, so we can definitely say it's a relation, because a relation is a set of any ordered pairs. But we have to determine if it's a function. Well, let's take a look at the domain. So what's the domain going to be here, and how do you determine the domain? What would you do to determine the domain? Count all the x values? Okay, we've got 5 x values, okay? The domain is where we list each of our x values, so what would those be? What would each of the x values be? Starting on the farthest, you can go to the left, yeah? -4, because this point is -4, comma 5. So why don't we actually put the coordinates down for each point? That might help us determine the inputs and the outputs. So what would my next point have for coordinates? -2, comma 2. Thank you. And what about this point right here, which you could miss? 0, 0, the origin. This point here is 1, 4, and then finally we have 1, -2. So we have, for our domain, we have -4 as an input, we have -2 as an input, 0 as an input, and 1 as an input. For our range, what are our different outputs? Starting with the smallest, working our way up to the largest. -2, okay. Yeah, go ahead, Colton. 0. Yeah. 2, 4, and 5. Okay, so the minute you see that there's 4 elements in the domain and more elements in the range, you know you're in trouble. It's okay to have it reversed, but that means that one of these elements, one of the inputs, has to have 2 different outputs. And which input is that? 1. Look at 1. 1, if I was 1, I don't know what my identity is. Am I 4 or am I -2? So this is definitely not a function. So it's not a function because 1 has 2 outputs. The input 1 has 2 different outputs. Okay. All right, so if you're looking at 5 points like this on a graph, is there any kind of visual test you could do or way you could look at that and know right away that it wouldn't be a function because one of your x values would have 2 outputs? Is there a visual way? Check if they're on the same line. Which line would that be in this case? 1, x equals 1, right? So the line x equals 1, remember, is what we call a vertical line. And notice if I draw a vertical line through x equals 1, every point on this line has 1 as its first input or coordinate. But notice it hits 2 different outputs. This is what we call the vertical line test to see if something is a function or not. Okay, so that's a great quick way of determining whether any graph or any relationship where we have a set of ordered pairs is a function. So let's formally define that. So here's the formal definition. And this is important that it's if any vertical line, not some students just say, oh, if a vertical line. It's not a vertical line. It's any vertical line. So you have to imagine sweeping across your graph, literally sweeping across it from left to right with as many vertical lines as you can see or draw. And if any vertical line intersects the graph in more than one point, the graph does not represent a function. So this first graph is a function because any vertical line I put through this graph touches that graph in one and only one spot. So for each x, there's exactly 1 y. Whereas this next function here, wish I could find like a pointer. I lost my pointers when I used to be able to point. This particular function, notice how it kind of curves back in on itself and then back out. If you draw a vertical line right through here, this, whatever x value this is, you have 3 different outputs. So you're really confused. Okay, so this is not a function. Okay, so I want you to use the vertical line test at your seats and determine whether each of these 3 graphs represents a function, yes or no. Oops. Oops, what did I do? The first graph is a function because if I draw any vertical line down through this function, I'm going to hit my graph in one and only one spot. So yes. So let's assume I don't have a scale on this first graph. Let's assume this point right here is a comma 0, whatever the value for a is. What would my domain be for this particular function? What would the domain be? You can use interval notation to help you, since we don't have individual coordinates or individual names. Eddie? You could say, yes, you could use set builder notation and say it's the set of all numbers x such that x is greater than or equal to a. That would be one way to represent the domain, because you're going to start here and you're going all the way this way for your domain. How would you use interval notation? How would you use interval notation, which we learned the last Wednesday? Where do we start? What's the x value we start with? A. Are we including A? Yep. So we use a bracket. And where do we end? We don't. It goes to the right forever. So that's how you would represent the domain in terms of interval notation. Huh? Did you for your homework? So do you have it now? Okay. Okay, good. All right, range. So look for your smallest y value. What's the smallest y value here? 0, right? So we start at 0 for our range. So our range goes in this direction. Look, we go in this direction. So our smallest output is 0. What's our largest output? There isn't one. It goes to infinity, right? So comma infinity. So that's how we would represent the domain and the range. All right. Let's talk about the next one. Function, yes or no? Did anybody get confused on this one because of this open circle and the dot? Nobody got confused? You did at first? Right, so let's suppose we put a vertical line in here. Let's suppose I drop a vertical line straight down through x equals 2, all right? Now, notice the only ordered pair of coordinates for x equals 2 is this solid dot right here. Let's say that that's 2, 1. We'll just make a guess. 2, 1. Up above here, we have 2, but it has an open circle, which means whatever equation is defining this curve right here, it stops when x is 2, and then from 2, 1, we get this like upside down, it looks like parabola. This is what you call defining a function in 2 parts, right? There's 2 individual pieces. From 2, below 2, you've got one formula that predicts your picture or your graph, and from 2 to the right, you have another equation or formula or model that predicts it. So this is definitely a function because 2 is well defined. I know 2's output, it's 1. Even though there's that open circle above it, it's not defining an output value. And what about C? Anybody agree with Mason? Okay, so we can if we drop a series of vertical lines down through this graph, we see that we hit it in more than one spot. And this is why we don't say a vertical line, because look what happens if I drop a vertical line right at the y-axis. How many places does that hit the graph? Once. So that's why we say any vertical line, not a vertical line. So this is definitely not a function. Okay. Any questions on functions graphically determining whether they're a function or not? All right, let's move along. This is a lot of language. Okay, most of the functions that we work with in this course are going to be expressed as equations rather than a set of ordered pairs. So in lecture 1, we worked with this equation where y represented the average cost of tuition and fees for public U.S. colleges and for the school year ending X years after 2000. So I think many of you might be familiar with this terminology, but let's go over it just in case. So if we have an equation like this, let's just write it down right here. Y equals 4x squared plus 341x plus 3194. We know this was a model representing the data. It didn't go through all of the data points, but it's as close to the data points as we could get it. It's a parabola. And we call the variable x the independent variable because it can be assigned any variable from the domain. That makes sense here. We're not going to say a domain would be negative 100,000 because our domain starts with the school year ending right here, ending years after 2000. So we're going to be 0, 1, 2, 3, 4, 5, just like you like it. All of the whole numbers would be in our domain. Those are non-negative integers. Okay, so that's our domain for this one because it's implied. This is what we call an implicit domain. If you were looking at just this function all by itself with no story behind it, you would say, I can put any value for x in there. I could put in square root of 2 if I wanted. So if you were looking at this equation without a context or a story, the domain would be all real numbers. But because this has a particular story where x is the years after 2000, the years ending x years after 2000, our domain will be 0, 1, 2, 3, 4, 5, 6, 7, whatever. Okay? So this is called the independent variable. Y, the value of y depends on what you put in here for x. You put in a number for x, out pops a y. Okay, so we call that the dependent variable. And the value of y is found once you select a value for x and you evaluate your expression on the right-hand side. Okay, so this determines a function since for each value of x is one and only one value of y. Okay, so your book's going to give you a few little questions like this for homework, so I thought I'd go over it. If you're looking at an equation and you solve for y in terms of x, and there are 2 or more values for y, then the equation is not a function. So let's take a look at this first equation. Does anybody recognize what kind of equation this is? If I were to graph that, what kind of picture I would get? 3x minus 2y equals negative 12. Does anybody recognize what kind of graph you would get? It's standard form of what? Linear. It's a linear equation. Once we solve this for y, we get it into that more familiar form, y equals mx plus b. So let's actually solve this equation for y to determine if it's a function. So we subtract 3x from both sides, and we get negative 2y equals negative 3x minus 12. Let's scoot that up here. Now we're almost done. We now have to divide both sides by negative 2, everything on both sides by negative 2, and that leaves us with y equals 3/2 x plus 6. So there's your familiar form, y equals mx plus b, where m is your slope and 6 here is your y-intercept. 3/2 is your slope and 0.6 is your y-intercept. So notice for each x you put in here, you're going to only get exactly one y value. So this is definitely a function, yes. Okay. Does anybody know what the next picture would be? X squared plus y squared equals 16. I'm not really expecting that you would. I just was wondering if you happen to know. Okay, this is a circle, but suppose you didn't know that this was a circle. So if it's a circle and you use the vertical line test, what's going to happen? All right, you're going to be in trouble, right? It's a circle with radius 4. So if I could draw a perfect circle, which I can't, but if I had a circle here with radius 4, perfect circle, I mean, you can see why I'm not an artist, okay? So why did I know it had a radius of 4 coming out from the center? Because if I take the square root of that number, I'm going to go out to 4. You don't need to know this. I'm just showing you. So if I had a visual, I could definitely see this isn't a function. So what happens is if I draw vertical lines through various parts of this circle, I hit it in 2 spots. So what does the corresponding algebra look like that shows me the results of that visual picture? So I'm still trying to solve for y here. So what's the first thing I'm going to do if I'm going to try to solve this equation for y? What will I do first? Let's get rid of what? X squared. Okay, let's get rid of that. And we'll leave y squared all by itself. We're still not done, but we're almost there. And now to get y all by itself, what must I do? Square roots of both sides. Remember, the square root of y squared is absolute value of y, which means you have two results, plus or minus the square root of 16 minus x squared. So right away, you can see the y value is positive, whatever you put in here for x, and minus. So you got two different y values for one value of x. That is not a function. This is definitely not a function. And if you ever want to graph, this is just a little off, but if you want to graph on a circle in your graphing calculator, then you have to do it in two parts. You have to do the upper part of the circle, this upper part, which is plus the square root of 16 minus x squared. And then you have to do the lower part, which is all your negative values, negative square root of 16 minus x squared. And that way, if you put both of those together, you'll get a circle. You also have to change your window to a square instead of a rectangle so it doesn't look like an oval.
I have a question.
Yep.
My function both is positive and a negative equation. I remember the graph. I got a circle, but it's broken towards the x-axis.
Yeah, they don't. That's just because your calculator doesn't do every single spot. It just connects from. It picks values, Mason, and then it connects them with teeny little straight lines, and it's just skipped over that. That's all.
Because I know when you get one of those like, and then on the other side they have like that line in between, and we don't draw.
Oh, it's not a vertical asymptote, no.
Because I know they draw that line with
Yeah,
the chin, so it's
yeah,
kinda
yeah.
awkward.
No, it's yeah,
Don't draw.
yeah, right. It's just that they don't do a continuous like trace it all in. They just do itty bitty points, and then they connect them with little. All right, so let's take a look at functional notation, and this will be the last thing that we cover. So now we're looking at a function as a table, not as a graph and not as an equation. It's given as a table. And this shows us the height of a baseball over time. So initially at time 0, my baseball's 3 feet high. So this is either right as it comes in to hit the bat, it's 3 feet off the ground, or I might be in Little League and have a tee, not Little League, what do they call that before Little League? T-ball, right, of course, T-ball. I might have a tee, and that might be 3 feet off the ground. So as you can see, as time goes by, my height gets higher, it reaches some maximum height, and then it starts to fall back down to earth. Okay? So the values listed in this table represents a function. We say that y is a function of x. If we call the height of the baseball y and time x, we say that the height depends on what specific time I'm looking at. So this is where we're going to drop the y equals notation, and we're going to use functional notation. Functional notation just really emphasizes for us that our dependent variable really depends as a function of our x value. And we often use these letters, small case f, g, or h. These are the most common, or capital F, G, or h to represent a function. Okay, so we can represent the function above by using this notation. Y equals, my output is a function of x. My output y is a function of x. So when you see this notation, f parentheses x parentheses, that's just like what we used to call y. It's an output value. Both of these are outputs. This is your output, and this whole thing represents an output. Right? And we read that notation as f of x. It doesn't mean f times x, because when you first learned algebra many, many years ago, you learned that when you have parentheses with two letters or a number and a letter, it meant the operation multiplication. But with functions, that's just a way of saying that my output value depends on my input value x. I'm a function of x. Okay, so in this particular case, what would be my input? What would I be putting into my function? Yeah, and what is the input here? 0 is one of them. let me say this better. What would be the units of my input? Time, and what's that measured in? Seconds. So my input would be some number of seconds, and my output would be some number of feet, right? It's always a number that goes in here, at least in this particular table. All right, so let's take a look at evaluating functions. So we have a table. We don't have a graph and we don't have an equation. It's a table. So we have this notation here, f of 2. So this says my input is 2. So I go over here to my table and I look at what's happening at 2. My input is 2 seconds. What does f of 2 represent? It represents the output, which is the height of the baseball at 2 seconds. And what's the answer? 99. Okay. Notice no units on that. These are just numbers. What ordered pair, if I were to start to graph this, what would be my ordered pair that's defined right here? What would my ordered pair look like? 2, 99, right. My input's 2 seconds. My output is 99 feet. So this is asking us to find the output, the height of the baseball in feet when the input is 2 seconds. So to interpret this, I would say at 2 seconds, my baseball is 99 feet above the ground. Okay, how about f of 0? F of 0, 3 feet. So f of 0 is the number 3. And if I asked you for an interpretation of this, what might you say? Anybody? Let me know. Raise your hand. Kenneth? 0,3 would be the ordered pair. What about a sentence that interprets what that notation means? F of 0 equals 3, given our context here, our story. Colton? Right. At 0 seconds, the baseball is 3 feet above the ground. Now, there's another way you traditionally will see this type of interpretation. Whenever your input is 0, in this case, say 0 seconds, we use the word initially. The word initial can be replaced by t equals 0 or x equals 0. So another interpretation is the initial height. So you see, when you use that word initial, it means this right here. It takes the place of 0 seconds. The initial height of the baseball is 3 feet above the ground. Okay, that's another way to say f of 0 equals 3. Okay, now it's a little twist here for the next one. Now what are we looking to find here? What do we know and what are we looking to find? What do we know here? Excuse me? Right, so here you're given the height, you're given the output. So now you know your output, or what we traditionally call y, but we're calling this now f of x. And we're trying to say at what time would my baseball be 103? So now you're going to this part of your table, you're looking up here and then looking for the corresponding x. So it's 2.5, and you can interpret that at 2.5 seconds, blah, blah, blah. All right. So now you write your ordered pairs like this, folks. Instead of x comma y, you write it like this. That represents your input and your output value. Okay? Input and output value. So this is your input value. And all your inputs come from your domain. F of x is your output value. And all your output values are in your range. Okay. Any questions before we move along? I think that's it, I hope, is it? We got one more? Oh, we got a picture, right? Okay. Oh, this is where, right. So we've got the table, and now we've got the same relationship about the baseball represented by this equation. Notice, if x is 0, what's the height of my baseball if I cover this all up with both hands? 3. So this is the equation that represents the table, the values in the table we just looked at. So if we were to use the equation to find f of 2, then what we would do is we'd say f of 2 is replace every single x value with the number 2, and then evaluate the expression on the right-hand side to get my height of the baseball at 2 seconds. So let's see, we get negative 16 times 4 plus 160 plus 3. That equals negative 64 plus 160 plus 3. And that equals 99. And does that agree with the table? Yes, it does. Yes. Use the equation to solve f of x equals 99. So now notice my output value is 99, as Kenneth noticed earlier. So now I set my left-hand side of the equation equal to 99 because that's my output. And now I have to solve for x. So now I have to solve what kind of equation? Right, quadratic. So to solve a quadratic equation, I have to have everything equal to 0 before I start. And I notice that 16 is a common factor all the way across, my GCF, my greatest friend. And since I like to factor things that start with x squared, I'm going to pull out negative 16. Oh, negative 96, thank you. Okay, so we pull out a negative 16 as a greatest common factor, and we get x squared minus 5x plus 6. Is that right? Have a seat. You can bring that up. Have a seat. Okay. And now we can factor this. X minus 3, x minus 2. 16 doesn't have a variable attached to it. Negative 16 will never equal 0, so there's no solution because that first factor here is just a constant. So the only solutions here will be when I set each of these factors equal to 0, and I'm going to get at 3 seconds and 2 seconds. I'm going to get 2 answers. So let's see if that agrees with the table. Let's take a quick peek back. At 3 seconds, I was at 99 feet, and at 2 seconds, I was at 99 feet. Cool. So that agrees. Okay.
I didn't see the negatives for 16.
Yeah. Yeah, you can still solve it, but it's harder.
I solved it as if it was
Okay. The other thing you can do right now, if you want, is you can divide both sides of the equation by negative 16. Since negative 16 is never part of the solution, you divide 0 by negative 16, you get zeros. And then when you divide each one of these by negative 16, you just get that, x squared minus 5x plus 6. So that's another choice you have. Never divide by the variable, but you can divide by a constant on both sides. Okay, the same thing is true with an equation. I blew your equation up because I realized you couldn't see it very well. So I blew it up here for you to see. So how do we evaluate f of 4? F of 4 says my input is 4. So literally you draw a vertical line straight down through 4. And there's your answer. At 4, you're at 50, does that say 57 or 67? 67 feet. So f of 4 equals 67. So you can also use your graph to evaluate functions. And similarly here, use the graph to find all solutions. Notice it's plural to f of x equals 67. So now what kind of line do I draw? Horizontal, right across 67, right here. And I note there are two spots, two values of x, 1 and 4. So if you were solving that equation algebraically, you'd be solving a quadratic equation because you'd have two solutions. Okay, you have about 13 minutes to start working on your group activity.